In chapter 9, in the first module, we shall learn about the Gauss and Codazzi Mainardi equations for a surface. And in the next section, we shall learn the relation between first fundamental form, second fundamental form and third fundamental form. Gauss and Codazzi Mainardi equations are the application of the second order tensor derivative of x I alpha. X I alpha is a surface vector and its tensor derivative x I alpha comma beta is equal to b alpha beta xi I, which we have seen in our previous chapter by the Gauss formula. So, here we shall deduce the Gauss equation and Codazzi Mainardi equation for a surface. So, now in module 1 of chapter 9, first we shall deduce the equation of Gauss and the equation of Codazzi Mainardi, or sometimes it is only called Codazzi equations, which is actually the application of second order tensor derivative of x I alpha. So, let us see how it is coming out. From Gauss formula, we have x I alpha comma beta equals to b alpha beta xi I. So, this is the expression obtained from Gauss formula. Now, taking tensor derivative to 1, we get x I alpha comma beta gamma equals to b alpha beta comma gamma xi I plus b alpha beta xi I comma gamma. That means, we are taking the tensor derivative with respect to u gamma. Now, we can apply Weingarten formula for the second term and we get the above expression will reduce to this form: x I alpha comma beta gamma equals to b alpha beta comma gamma xi I minus b alpha beta a rho nu b rho gamma x I nu. So, this one is the expression substituted from Weingarten formula. Using Weingarten formula in the above equation, we obtain x I alpha comma beta gamma equals to b alpha beta comma gamma xi I minus b alpha beta a rho nu b rho gamma x I nu. That means, xi I comma gamma is replaced by the expression in the right hand side from the Weingarten formula. Similarly, if we interchange beta and gamma, we get x I alpha comma gamma beta is equal to b alpha gamma comma beta xi I minus b alpha gamma a rho nu b rho beta x I nu. So, subtracting these two equations, we get x I alpha comma beta gamma minus x I alpha comma gamma beta, and in the right hand side we obtain this one B alpha beta comma gamma minus B alpha gamma comma beta xi I. So, from the first term xi I is taken common. So, it is coming to this expression, and from the second term we take xi nu common, and the above expression is coming to B alpha gamma A rho nu B rho beta minus B alpha beta A rho nu B rho gamma. Now, if we write xi alpha comma beta gamma minus xi alpha comma gamma beta. Now, as we have taken the second order tensor derivative and we are taking the difference of that. So, a curvature tensor will evolve, and this will be equal to xi rho r rho alpha beta gamma. So, putting the value in the left hand side, we get xi rho r rho alpha beta gamma equals to on the right hand side. Now, multiplying 4 by xi I, we get xi I xi rho r rho alpha beta gamma equals to B alpha beta comma gamma minus B alpha gamma comma beta into xi I and xi I plus the right hand side with the expression given in equation number 5. Now, since xi upper I and xi lower I equals to 1 and xi sigma xi I equals to 0, that means any term like this xi rho xi I or xi sigma xi I, it will come to 0, because xi I is the surface normal vector and xi sigma is a surface vector, and so they are orthogonal. So, therefore, xi sigma xi I equals to 0. So, the right hand side, the second term will vanish, and the expression in the left hand side will also vanish, because xi I xi rho is equal to 0. So, we get B alpha beta comma gamma minus B alpha gamma comma beta equals to 0. So, this equation is known as Codazzi Mainardi equation, or sometimes only Codazzi equations. Here alpha beta gamma all will vary from 1 and 2. Now, from the above expression, that is from equation 6, we can see that there are only two independent Codazzi equations are there, and they are B 11 comma 2 minus B 12 comma 1 equals to 0, and another one B 22 comma 1 minus B 21 comma 2 equals to 0. So, these are the only two independent Codazzi equations. All other equations are dependent with this, because alpha beta gamma all are running from 1 and 2. Now, again multiplying 4 by g I j x j sigma, we obtain the above expression Gij xj sigma xi rho r rho alpha beta gamma. In the left hand side we are obtaining this, and in the right hand side we are getting this expression. And we know that Ji xj sigma is equal to 0. So, the first term in the right hand side is equal to 0. So, only the second term in the right hand side will be there. And also we know that Gij xi rho xj sigma can be written as A rho sigma, and similarly for the right hand side Gij xi nu xj sigma can be written as A nu sigma. So, putting these values we get this form A sigma rho, because A sigma rho is a symmetric covariant tensor. So, we can write A rho sigma or A sigma rho r rho alpha beta gamma equals to this expression. Now, taking the inner product with that A sigma rho in the right hand side and in the left hand side. So, from the above inner product we are getting r dash sigma alpha beta gamma equals to B alpha gamma B rho beta minus B alpha beta B rho gamma. Therefore, if we express in this way, that r dash sigma alpha beta gamma will be equals to B sigma beta B alpha gamma minus B sigma gamma B alpha beta, where sigma alpha beta gamma is running from 1 and 2. This equation is known as Gauss equation. And the independent Gauss equation is r dash 1 2 1 2 equals to B 1 1 B 2 2 minus B 1 2 B 2 1. Now, as B equals to B 1 2, we get r dash 1 2 1 2 equals to B 1 1 B 2 2 minus B 1 2 square. That means, the determinant of B alpha beta, which we denote by B. So, r dash 1 2 1 2 is nothing but it is the determinant of B alpha beta, where B is the determinant of B alpha beta and alpha beta is running from 1 and 2. So, the Gaussian curvature, which we have defined earlier, that it is r dash 1 2 1 2 by A, and it will come to B by A, where K is the Gaussian curvature of the surface. So, we can calculate very easily the Gaussian curvature of a surface by taking just the determinant of the coefficient of second fundamental form and the determinant of the coefficient of first fundamental form. So, K is nothing but B by A. And we always know that for a surface A is always greater than 0. Therefore, the sign of K depends on B. So, that is why the second fundamental form is important, that the sign of K depends on B. Now, if K the Gaussian curvature is less than 0 at a point on a surface, then that point is called a hyperbolic point. So, here it is the surface of negative curvature, that means Gaussian curvature is negative at the hyperbolic point. If k equal to 0 at a point on a surface, then that point is called a parabolic point, and if k greater than 0 at a point on a surface, then that point is called an elliptic point. So, for k greater than 0, the surface is a surface of positive curvature, and for k less than 0, the surface is a surface of negative curvature. So, the elliptic surfaces are the surface of positive curvature. So, this type of classification we will again study in later on when we will study the Dupin integratics. Now, let us find the relation between first, second and third fundamental forms. We have obtained first fundamental forms, we have obtained second fundamental form, and we have obtained also third fundamental form in our previous sections. Now, we will study here a relation between these two forms with the help of this Gauss equation. From Gauss equation, we have r dash rho alpha beta gamma equals to b rho beta b alpha gamma minus b rho gamma b alpha beta. Again, from the definition of the Gaussian curvature, we know r dash rho alpha beta gamma equals to k epsilon rho alpha epsilon beta gamma, and equating these two equations we get this one, k epsilon rho alpha epsilon beta gamma equals to b rho beta b alpha gamma minus b rho gamma b alpha beta. Now, taking inner product with a rho beta, the associate tensor a rho beta, from both sides we get this expression. Now, after the calculation in the left hand side, we get the expression in the left hand side is coming to k a alpha gamma equals to, now in the right hand side, a rho beta b rho beta is coming to 2h, because from the definition of mean curvature we know that the mean curvature h is equal to half a rho beta b rho beta. So, we are replacing a rho beta b rho beta by 2h and then b alpha gamma minus, and that expression is equal to c alpha gamma. So, taking product with du alpha du gamma, we get k a alpha gamma du alpha du gamma equals to twice h b alpha gamma du alpha du gamma minus c alpha gamma du alpha du gamma. That means, we have obtained the three forms. For the left hand side, a alpha gamma du alpha du gamma is coming to the first fundamental form. B alpha gamma du alpha du gamma is giving the second fundamental form, and C alpha gamma du alpha du gamma is giving the third fundamental form. So, putting the expressions for first fundamental form, second fundamental form and third fundamental form, we have K A equals to twice H B minus C, or we can write in this equation form that C minus twice H B plus K A equals to 0. So, this is the relation between first, second and third fundamental forms. So, in module 1 of chapter 9, we have learned two new concepts of surface geometry. The first one is the Gauss equations and Codazzi Mainardi equations for surface, which are nothing but the application of second order covariant derivative or tensor derivative of xi alpha, which is also the surface vector, and from there we have established a relation between first fundamental form, second fundamental form and third fundamental form. So, with this we end this module of chapter 9.